Let me see. I'm going to send a reminder to Pedro. Actually, I think it's the same one that I think you already got that. He already got that invite.
No problem. Um, so did Pedro talk to you about my project? Because he, like we had a meeting last Thursday, or
Yeah.
yeah, last Wednesday or
No,
Thursday.
no, he did not.
Okay, all right.
So I would certainly be happy to hear about that.
Okay, so the thing is, I think after we talked about the project's progress, I think our understanding on the parser seem to be a little different, so we want to hear some advice from you. That's
Okay.
yeah, that's why I'm so
I
eager to
mean,
talk about this.
do you want to talk to me, just to me, or do you want Pedro to be there?
I think yeah, probably if he was there, that would be better because
Okay.
yeah, you can hear like opinions from both of
All right.
us.
Well, so what I would suggest then is we do a little bit of lecture and exercises. And if he joins us, then we'll switch to going over that. And if
Yeah,
he doesn't join us,
perfect.
then you'll just present what you have, and I'll talk to him
Okay.
separately because I want to
Okay,
make sure that
okay.
we get through it today. Uh, but but maybe he'll join a little late, and in that case, we're fine. We'll have it.
No problem. If he didn't show up, I think I could just try to narrate his opinions
Right.
to you as well.
Sure.
Yeah.
So this would be lecture 11 now. Time is passing quickly. And I wanted to do a little bit of work on explicit forces. I know I did assign a separate homework assignment because I wanted to give you time to, there he is. Um,
Hello.
Perfect timing.
Great.
We were just saying if you came, we would start by talking about the project, and if you didn't come, I would lecture first, and then we would talk about the project.
We can talk about the project.
So, do you want to screen share? What? How do you want to organize?
Uh, okay. I think I could screen share.
Okay,
I'll
let me
just
make sure everybody's got screen share privileges. I think everyone does, but okay.
help.
All right.
Oh, okay.
Well, let me unshare. See, it looks like I'm not screen sharing, so I should. Am I screen sharing, Pedro? No.
She's sharing.
Okay,
Yeah,
that's
I'm
good.
sharing it. Um, let me just give a quick demonstration on it first. Wait, where's my terminal? This one? Okay, and also this one. Okay, so the first the first thing that we need to do is to enter this CC3D builder. This is a directory that stores the Python files for us to inject our rules. So for example, uh, just to type that. So by running this Python file, and this is the pro like the project, this is the directory, and now we could just give these rules IDs. For example, if I'm going to write the seventh rule of this project, then I'll just call it. And if I'm going to create a cell type, which is called cell new 7, and just let it grow because the behavior that I designed are only includes growth and differentiate. Let's start with the simple one. and there are 4 ways to control when the behavior would happen. So you could use the threshold of a kind of field. For example, the field that already existed in the project is oxygen. So you could use that. And of course, you could just use the time limit to control it, and also like the probability, like how likely is this going to happen. So let's just use time
So
limit.
one thing you have to be careful about with probability
Mm-hmm.
is that you have to have you can only express probability per time
Yeah,
because you're going to have to rescale it with the uh, with the Poisson rule to if you change the time reference, right? If you say that the probability is 50% per hour, and then you changed from hour to minutes, you have to rescale that number. It's not just 1/60th of that.
yeah. Now it's arranged like the probability refers to the
One Monte
probability that
Carlo
happened
step.
one. Yeah. So
But I
um
would build in already the idea that you have a concept of so all of these things really do require the concept of knowing what the time scale of one Monte Carlo step is. And so I think you need to have somewhere a definition of one Monte Carlo step is so much time, real time, so that
yeah.
if the user changes it, it rescales automatically.
So
Now
I
that
think
maybe that's too much for version 0, but I think that I would be planning that from the beginning because I guarantee we'll need to do it. And so I don't know, Pedro, how you feel about that, but to me, one of the problems in CompuCell is that we don't have units associated with things in an automatic way. And this would be a way to begin to fix that problem.
I'll give some thought to it. I think you have good points.
I don't think it's that difficult. I mean, most of these things, the threshold doesn't care. Um, the logical block doesn't care. Uh, the time window does care, but it scales linearly. The only one that requires a little bit more is the probability per unit time, and then you apply the Poisson ratio rule and correct it by the time. So
But
I don't think it's
I don't necessarily understand like just by the name probability how the change is happening here.
right. That's why I would say probability per time, right? And time window is not time window. It's right. It's a timer. So it's the um,
But even then, like probability per time of what happening.
of the
um
event.
yeah, for example, we have differentiation here. So that means like in the future simulation, the probability of the differentiation happening would be the value that you assign here.
So maybe instead of where you say could select condition type, if you said condition trigger type,
Condition tripped. Okay.
right? Because it's the thing that activates the event, right? I
Yeah.
mean, again, Paul and I use slightly different language, and we should probably follow Paul's language, even if it's not the one I use. But I would say this, what I would call these are events and triggers. So there's some
Yeah,
event,
that makes
and you want to
sense.
know when the event occurs. It could occur when something is bigger than something else or less than something else. That would be a threshold. It could occur after some amount of time. It could occur with some fixed probability or variable probability per unit time, or it could occur on some other external logically defined signal. And all of those are reasonable One question, and I don't know how Paul handles this for events, is does the event trigger multiple times if the condition is satisfied continuously?
Oh,
Or
we
it only
have
triggers once?
arrangement afterwards. So can we just like continue writing all
Okay.
the rules?
No, I'm sorry. I didn't mean to be difficult.
Yeah,
I just
okay,
wanted to
okay.
understand. Okay,
Okay,
go ahead.
okay, yeah. This one is involved into our consideration. So I'm just
Right.
um okay, I'm just so let's say it would start at 500 molecular step and will and because growing is a continuous process. So
Right. So you have
and
to have a range of times.
this is the mathematical model we used to. So the regulator here we use the oxygen concentration
So the
as the
model, sorry, the
mm,
model here is the rate, is determining the rate. Is that right?
yeah, yeah, like for the growing processes that means the oxygen concentration would define the delta.
Right, I get it. Okay,
Okay.
and
So
okay, and
here
you
just
and
another.
number three would mean you can write a free expression. You can write any form you want.
Yeah, but here it's more like polynomial.
Okay,
So
that's fine.
mm,
Okay. And this is already a lot, so I'm not trying to, you've already done a great deal here. I just want to make sure I understand what,
okay. Yeah, because I didn't write a detailed explanation for you.
right.
So here it was just as it will be like triggered once where so for growing it would be like a continuous process. So we just type no and debug mode no.
So
And
what are Y min and Y max?
why oh this is the Hill function parameter.
Oh, your display, it's the vertical displacement. So it's the Hill function plus or minus.
Yeah, like why this is part of the Hill function formula. So you
Okay.
could
So
just
if
um
you
uh,
set the Hill function, James, when you have a parameter for y max and y min, if you set the max to 0 and the min to 1, it's an inhibitory Hill function.
Right.
So the max and min are misleading. So they would be like the left
X equals
limits
0 and X
and the right,
equals
yeah,
infinity. Okay.
yes, the left and right limits, yes.
All right. Fine.
okay,
Okay.
so probably we could just adjust it
We can rename
properly.
these. That's all right. That's
Okay. So here it just reports that we didn't have this in our XML before, so we need to create new types.
oh, good. So
So
you've got the registry now, the variables and
yeah,
parameters.
like we need to. So one tricky thing here is in our previous model where this situation could happen because we put the volume constraint in the XML file. But
Mhm.
if we're doing behavior such as growing, or we need to we need to change the target volume in our steppable file. So we need to remove the volume constraint in the XML
Right.
and then just put all the contents in our steppable start part. So yeah, so
So it should really throw an error, but that's asking a lot, right?
yeah, so we need to take this into consideration. And here actually like I designed a streamline or pipeline to do this process, like to do this automatically. So if we create some new cell types and we need to um change its volume for
Yeah.
relevant things, so we need to do this. And this is the lambda. So here it just reports. Okay, and then
Oh
uh
boy, so it actually rewrites the XML.
yeah, and also for the so yeah. See. Oh, just a second, let me check. So previously I created a lot of um
Rules.
cell type here because for debugging. So
Yeah.
yeah, that's also an issue because every time you do some attempts to modify this project and it would just keep all the records. So it's good it's just kind of like have a memory here.
Right.
So the new cell type we created is this. Let me change the color. So
I was just talking to Michael about how we really need I mean, it could be JSON, it could be XML to specify the cell configuration. In other words, you should have each cell type should have when you serialize it, it should have the cell, its position, the pixels belonging to it, a list of all its properties, and so on. Um, Cell by
yeah,
cell and cell type by cell type, so that you actually have a reusable specification. And you're doing a lot of that here. Um,
forgot
Now,
where
yeah.
the position here for initialization, their position are set to be randomized. So
Mhm.
you could just show up everywhere in this domain.
Right.
So for the cell new type, I guess is this one. But after you quickly run this, you can see like some cells disappear. That is because when I write in these cells, I didn't actually accomplish the whole process. So we report error, and then it didn't execute to the step to writing their lambda volumes and target volumes, but the cell's definition has been created in the XML. So that means for these cells, we didn't create a lambda or target volume for these cells, so they just
So
disappear.
set to zero. So it was set to
Yeah,
zero.
so they'll just shrink. But for these cells that we succeed in creating them, like the whole process is accomplished, they could just survive in this domain. Yeah, I guess this is for the, and you could see, uh, this Monte Carlo step. We said it would just start from 500 Monte Carlo steps, so let's see. Yeah, so it's growing. That means the rules is successful. And for there are some other cells that I said would be start growing from the 1000 Monte Carlo steps. So it's also working for the for that cell. So for growth, growth is a really simple process, so it will be really
Right.
easy to finish this whole
So,
process.
so to understand, you have a hill function of what in this case? So in this case, it just grows at a constant rate when it triggers.
No, it's not a constant rate. Oh,
So the
oh,
hill
in this
function is
case,
a hill
yeah.
function of what? Of the
Um,
concentration field.
yeah, concentration field because it didn't
Right.
move, so the oxygen oxygen
Right.
concentration for that cell is
Right.
constant, so it would just grow in.
Right. So, so one thing that Morpheus has that CompuCell doesn't have
Mhm.
is a named set of spatial relationships. So in
Mhm.
CompuCell, we have things like secrete at center of mass of cells, secrete at over the whole area of the cell, secrete inside the boundary of the cell, secrete outside of the boundary of the cell. So those are spatial concepts. Now, when you're saying read the oxygen field, you have to ask it, how are you reading it, essentially? In other words, where are you reading it? There, you have to have all of those, you have to have all of those options. They're not, maybe not to begin with, but at some point you're going to have to define a flag that says for a field, the values aren't uniform everywhere. So you have to decide how you're going to where you read the field. essentially.
I see. So yeah, for this case, I just used the concentration at the center of mass.
Right. That's a reasonable approximation, but you probably need to have a name tag that says which one to use. Um,
Okay.
and the other the other thing is, I mean, if you're responding to an external field and you don't change it, then that's fine. But if you're right, a lot of the time what we do is we do a absorbing step, right? We do an uptake, and then we use some function when we use that numerical amount that's taken up to control. And in that case, we have to have some, I mean, in principle, the amount uptaken is something handled by the user. And then there's a variable and you have a Hill function of the variable. Um, that's possible.
Yeah, so
And so,
yeah,
so
that
one reason one reason we never did this is because there are an awful lot of different combinations of ways you might do it. Although in fact, we almost always do it the same way. We almost always take up the material and then do some Hill function of the concentration, maybe with a resting energy. We have
yeah,
resting metabolism.
so that is I think that's real close to the issue that we talked about. So so my opinion, or should I say opinion, but viewpoint is um even though we're trying to simulate a very complicated process, we could just disentangle this compl complicated system into separate rules. Like like these behaviors pers are progressing steps. Maybe they could just happen um simultaneously, but if we set these different rules happening in one Monte Carlo step, I think it wouldn't be like it wouldn't have a very big difference. Um, and also I think the like when I was designing these rules, um, I think like one big difference that my design between my design and the Physicel is for Physicel um for each rule, it could only allow you to input one trigger, but I think we could just design multiple triggers. So if these triggers are connected with the logic and, so we could just put all the triggers as the regulator for one behavior. But
Yeah,
of course, like
yeah.
yeah,
Go
like
ahead.
so for that kind of situation, we have to design like probably multivariate linear model or multivariate Q
Right.
function to calculate the rate.
Right.
Um,
So then you have to have multiple basically patterns that you provide the user to do, or they have to be able to write free. They have to be able to write numerical expressions. Yeah.
yeah, so that also like leads to a problem. So if we wanted to um input the rules in a very large scale, like if we wanted to input over 50 rules, it'll be really hard to list all the rules in a list because there are so many sub choices, like sub options. Because for different behavior, we have different like subsequent options for the users to provide.
So you're worried that it's too cumbersome to do it this way because you have to keep going through the whole hierarchy by hand. I'm not sure
Yes,
what I'm
yeah,
not
so
I'm
I think, yeah, for precision, you could do that because for each behavior, there is supposed to be different designs, right? But I think I'm just kind of concerned that it will be deviate from your like starter point that you want the rules to be large scalely imported. So
so
like, yeah.
so what do you propose? I mean, do you think that you should have a pattern basically that say this is a default or a basic structure for the rule, and then you inherit that unless you specifically overwrite that pattern. That would be one way to do it.
Yeah, I think like offering a pattern for the users as a reference is,
Hmm.
yeah, it's really helpful and important. But still, like, it would have a challenge on the format, right? Because we would have diversified diverse formats of that pattern.
Right. Well, that's always the problem. In other words, if you want to make it easy so people don't have to type everything, then you have to give them structures that they could use. And then you have a lot of combinations. Whereas if you give them too much flexibility to type anything the way we have, then things don't become reusable and repeatable because you can't parse what was done.
Yeah, so yeah, so that is an issue here. Uh, so we just
Right.
and also like Pedro, you have some like advice on the process.
Yeah, I mean, I think your project is very ambitious and it's going well. I mean, I saw it working. I was very surprised positively. My only problem is that, like, if someone already has a module for cell differentiation, for example, your code will not simply add a hill function that changes a parameter that they have, and will instead add a new separate module of cell differentiation on top of their code. And that's so I think the average CompuCell user will not benefit much from your thing because they already have their modules. They just want something that adds in rules to modify the parameters that they already have. And this is something that any CompuCell user could use. Is this clear? James, did you get my
So
point?
what you're saying is that you want to be able to have as an input any variable or parameter present in the model, and as an output any variable or parameter present in the model.
Correct.
And um, you also want to be able to open an existing specification and view it and edit it. So then you have to have some sort of graphical or numeric or text representation of what the rules are. And you also want to be able to then read in a rule set and then modify the rule set rather than just start from scratch. Is that what you're saying?
I didn't understand the second part.
You want to be able to read in an existing rule set and modify it.
Yes. Yes.
Oh,
As
I
long as
see.
they are in the format. Because well, you can build in chunks with comments saying like rule list and in a comment, and the code can recognize these code chunks. So essentially, what the rule parser will do would write a cell dictionary with the parameter name and and do that for the a loop over all cells and do that the cell dictionary equals the hill function with the input parameters, the input variables. Essentially, that's all. So um,
Mm.
it would be agnostic to the mechanism, to how the user implemented the mechanism.
Well, so you're saying don't worry about the fact that it's cell growth. You just say that there is some variable in that has some input and then you have some output. And then it's up
Correct.
to the user to wire that into the target volume.
Correct. And otherwise, doing the way she has, we need someone to keep maintaining this code, because if you have one migration mechanism and I have a slightly different one, then she has to include both implementations in her uh, code assistant tool. Otherwise, at least one of us will not benefit from it. And if someone invents something else, like another cell behavior, she has to include this new cell behavior in her framework. And this is a lot of work. I'm not saying it is not doable. It is certainly doable. She has done for two behaviors, but it is a lot of work, like much more than I think for one
So you're
course.
suggesting a generic version of this, and then the user would have to write something that says read this value and apply it to the volume.
Yes.
Now, my suggestion, which was more of a change to core CompuCell, was to say, okay, we're going to have say that we shadow every CompuCell cell attribute with a dictionary entry. And then synchronize we automatically synchronize between the dictionary entry and the target values every Monte Carlo step.
Yeah, but I think that's the same thing I'm thinking. That's
So
what I have in mind.
in that case, you have an easier time because if the thing is really just a dictionary entry, you don't it does it behave. You don't care then whether the thing is a dictionary entry or whether it's got a special value meaning in CompuCell.
Yeah, the user is charged with assigning the dictionary value to the CompuCell built-in parameter. Yeah, the user
Well,
is
or we
responsible.
rewrite CompuCell so that the shadowing is done
Yes,
automatically.
exactly. Yeah, I prefer this approach which you suggested last class, I think. I prefer it by far than the others. Yes.
But it doesn't really change anything very much for what Shayu's been doing, because all it is not write one line, which is to say write the value from. She's got something which explicitly is changing the cell dot target volume. If her output is change cell dot dict quote target volume, it's only changing one line of her code generator, right? Now, the difference is that by itself, at the moment when you ran that, it wouldn't do anything. The target volume, the dictionary entry would change, but the target volume wouldn't. And so then you'd have to write a loop that updates the targets. Um, but I don't think that that's too big a deal. And whether you do that automatically or whether you do it, no, by hand, uh, well, I don't know. You have to think about that.
But James, in her code, her script creates a new steppables class with the behavior in it. So, for example, cell growth or differentiation. It's not only a rule.
Yep. So I'm adding the steppables when I'm writing these rules, it's already a paradigm, and I set all these fundamental behaviors as steppable. So if I'm going to, for example, I'm going to have differentiation behavior, then I would just add a differentiation steppable into the Python steppable file. And I think for the point on like leveraging GUI like tool to synchronize the parameters, I think if now we're storing these parameters temporarily in JSON file,
Yeah.
I think we could also like transform the JSON file or just build another like bridge to connect the JSON file with the GUI.
Right. Well, I would really like to have a JSON file that describes, every cell in the system. Okay, this is the name of the number of the cell. This is the locus of points in the cell. This is the properties of the cell, and so on. That we could use as a restart file. Have you ever used Pedro? Have you ever used the CompuCell restart functionality?
No, I'm afraid of these functionalities.
Well, but that's bad in a way.
Yes. I think once I tried to use the function pause simulation or stop simulation, I don't remember which one it was. And it crashed everything. And then I never tried again. But maybe I saw someone using the stop simulation command effectively.
No, but this is the restart function.
Yeah. No, I
Doesn't
haven't
that
tried.
write everything out in the form of a VTK file?
The stop function or the restart function?
Restart.
I don't know. I don't know. I haven't seen this function.
Well, it's actually pretty important, so I would find out. It's actually it's a critical thing because to some extent we're reinventing parts of that. Um, but what you would like is you would like to be able to have a text file that basically serializes the state of the simulation. And within that, you'd like to be able to have the rules that apply to that cell written out. Now again, the problem is not that you're doing it wrong. The problem is there are a lot of different right ways you could do this.
Mm.
Um, However, once you make a decision about those things, it's a little difficult to go back and change your decision about how to do it later, or it may be. You may find yourself locked in a little bit to how it works. And so I think that's why maybe it's worth thinking about it a little more. On the other hand, there's also an element of this where doing it at all as a proof of concept is useful, even if we wind up deciding we don't like the way it was done ultimately. Well, not like the way it's done is wrong. Even if in the end we decide perhaps there's another way of doing it that might be more efficient, you've still shown how to do what you can do. So I guess my question really is, but you say you create a new so how many new steppables are we actually getting here? Because you don't want to you don't want to, on the one hand, you'd like, all the rules relating to a given cell type. For real modularity, at some level, you'd want those to be living in their own steppable. Another way to do it is to say that that the that the how to say it that the rule specification, which is what you're doing here, the rule specification is modularized, but the Python that it compiles to is not. So that's another possibility. And that's actually how I was thinking about it, but that may not be right. I'm just a little concerned about what it putting, creating dozens and dozens and dozens of different stepables, I think will be potentially confusing and slow.
See, uh, yeah, so yeah, I didn't think of, like multiple cells, but having same behavior or same behavior type. So, um, for each behavior type, there's corresponding steppable. For example, for growth behavior, there's growth steppable. For differentiators, differentiate steppable. But I think by far, if you're going to create two cells and both of them are doing growth behavior, I think by far my approach to like implement that would be creating two growth steppables. But yeah, that definitely needs improvement because it's all necessary to
So, okay. So I guess the question is where, at what level is there modularity? And so if you have a specification where each cell has a JSON description of everything that the cell is doing, that's modular and that's very attractive. But it's not necessarily true that you have to compile that into, a separate steppable for every cell. So because, and I suppose you could. What steppable, not maybe. You certainly don't want it to be a separate steppable because that'll be prohibitively expensive. You could create a separate class for every cell. But if you do, intrinsically, my instinct would have been that this kind of approach would be prohibitively slow. But it is in fact exactly the approach that Iran takes with Vivarium, and it works very well. It's high performance. But of course, he doesn't integrate it through Python. But Vivarium does exactly that. It spins up a separate solver for every instance.
um I haven't tested that yet. Um but I think if there is a way to integrate them to speed up the compiling or the computation.
Well, I'm using the word compilation probably inaccurately. So let's just say code generation.
Mm. So in that case, if we integrate some the behavior that belongs to the same type, but with different cells, and of course there might be different regulators, um, that would be quite difficult because the code could be messed up, like messed up in order.
Right. So you want to basically say, here's the rule set for this cell, here's the rule set for each cell has its own rule set, which is reasonable.
Yeah,
Um,
and yeah, like cell could I would say a rule set is bounded to a cell type. instead of a cell has um one rule set, because I could probably show you my JSON file here.
Okay, that would be great.
You can see like
Can you
this
make
is
it a little bigger? Sorry, could
okay,
you zoom in?
great. Um, okay. So
Right,
this is JSON file, and this is for the type one. Oh, rule one. So you can see
right,
the ID and target. This is the cell type and growth mode, the starter. This is the condition trigger,
right,
and this is the model regulator. So
right.
I would say like that it's kind of like you assigned a cell for a rule instead of like ass assigned a rule to a cell.
That's fine because you can have the rule be a freestanding thing. I mean, in essence, you want to be able to do both things, right? You want to be able to define a rule and attach it to a cell.
Yup.
And you also want to be able to define a cell that has a bunch of rules attached to it.
Yeah.
And so I think I think that those are both and at some point, oh, a single file is probably going to only is going to be privileging the objects, the cells, or it'll be privileging the rules. Right? You could have a list of rules and say, give me a list of all the cells this rule attaches to. Or you could have a list of cells and say, for each cell, what rules does it have? And
Sure.
those should have the same information in them, but the way the data structure is different. I mean, of course, if you have a list of just pairs, which are rule, comma, cell it attaches to, then you can build both lists from that. If you just have a tuple, a long set of tuples, you can sort it in either way.
Yeah. Definitely.
Um, so target means the parameter that's being changed. Or
Oh,
target means,
it's cell type because this cell was created to observe the growth.
okay,
So just name it cell type.
all right, okay.
And you could see, so this is for rule two, rule four.
Yeah, I think this is attractive. I might, well, in a future version, I might add some additional fields to it. But yeah, I think it's impressive. I think it is worth looking at how Vivarium does this. And I don't know, I think Morpheus had a rule set grammar, didn't it? I mean, well, it has a full scripting language, but I thought it had a subset of that that was a rule script. So it might be worth looking at that.
Yeah, and I think this is just kind of one channel that could modify the rules JSON. And I
Right,
think if you want to change the parameter attribute, if you don't want to change the rule anymore, you're not going to inject any rules. Instead, you just want to make modifications on the parameters, for example, probably here and probably the hill function. And for the behaviors, you could even for the behaviors. So like originally they're stored in the Python steppables. You
right,
can also like write another channel to make modifications on that. It's just kind of like the physics are GUI because
right,
as far as I know, like that GUI reads content from XML, and
right,
then like after once you made modifications on the XML, it just stores one copy in the memory, and then it would just um send the content of the changed version to
Right.
cover the XML, just kind of like double channel thing. Um, yeah, so probably I think like and that's for the rule part. If you want to change the attributes part, I think that's another part. I think like that's another story that we can talk about. I think I could probably think about that later and also try to just make another part of code generator for that,
Yeah.
and finally like integrate them.
Yeah.
But
I
like
mean,
for
this
this,
is already a lot. I mean, you've already done really a lot here.
but this is
Um,
just like for two behaviors.
right.
So
Well, but that's why I think the generic thing of just of taking inputs that are dictionary entries and outputs that are dictionary entries. And then if you like, you could say, by the way, I want my output not to be dictionary, but my output is not only a dictionary entry, it also exists as a C++ attribute. So, but I think the thing that I really want is to be able to say, this cell has these rules. So of the kind that you have here. In other words, this JSON set, I'd like to be able to attach that to a cell type as a template.
okay,
And I'd like to be able to attach it to an individual instance of a cell. I'd like to be able to have a simulation that writes out, this is cell number 777. It has these rules associated with it.
okay, okay, that's okay. I see.
And and it's okay. I mean, I think it would be worth at this point. I think it would be at the worst worth at this point having Maciek and Pedro and Maciek and Peter and maybe TJ give an opinion about this. In other words, you have something that works, which is really impressive. And so now that it works, I would say the next thing to do is to show it to the core developers of CompuCell and say, if we were going to try to roll this out as an actual module in CompuCell, a distributable module in CompuCell, what do you think? And for the purpose of the class and the project, you don't have to do that. But I think for the purpose of actually producing something that's going to be the maximally useful thing for the community, I think it's worth having that discussion. But I think Pedro's right. One problem in CompuCell is that there's this distinction between dictionary entries and predefined attributes of the cell. And those predefined attributes of the cell are not really defined in a consistent way. So for example, the chemotaxis parameter for the cell, you have to reference with a get because it's associated with a field. You have to tell the chemotaxis parameter of the cell to which field. And so if you wanted to adjust the chemotaxis strength, the way you would call that looks different from the way the way you the way you call, say, changing the cell volume. So I guess I'm agreeing with Pedro that if you write code which says take information in the system and change a dictionary value, that's your output, then that will work no matter what happens to CompuCell later on. And then somebody else has to write something that says, okay, in the special case that this dictionary entry is the cell volume, I have to write cell dot target volume. I have to write this. So that second thing has to be changed as CompuCell changes and features change. But your code generator then is independent of those changes. It's separated from an implementation interface. And so I think doing it that way would simplify the situation a lot, because then your code doesn't break when there's a change to CompuSol. Now, can you show me the Python that this generates? What does this generate when you run it?
It's to the
In other
terminal.
words, what does the actual simulation that you were running just now look like?
Okay. Um,
Oh.
no. Where's the terminal? That probably just closed the terminal here. Even this terminal showing what's going on here.
No, but when you ran this code,
Mm.
it ran growing cells. I want to see the code that ran to grow the cells. It's not the JSON that's doing
Oh,
it.
okay.
The
Okay.
JSON is getting code generated into Python, I assume.
So there are this this is the rule project. So I have
Yeah,
like two parts. Um, and one part in the directory called CC3D Builder. It's attached to the source code of CC3D, and that is for writing the rules into the JSON file.
right,
And the remaining Python files that are attached to this project is for execute this JSON file.
right. So I want to
Uh,
see how that JSON file is executed.
okay, so my code probably will include some Chinese annotations, but
That's
so
okay.
so I have a plugin file. Um, so wait, I'm not sure like if it's okay to start with this level. Mm. So for each behavior, for example, because I only have two behavior here,
Mhm.
so I will have to plug in separate.
Yeah,
So for the differentiate behavior, there's differentiate plugin. Uh, apply block. Um, I think this is kind of the middle level. And I also like write, I mean like the steppables are predefined in the steppable paradigm file. So for example, for the differentiate steppable, so I have to assign the mitosis steppable because in the division I need to call some functions from CC3D. So I have to use the steppable or inheritate from that steppable. And I'll identify the keys in the JSON file.
right.
For example, like if this is the option that I chose for differentiation. So that is just simply
Right. Oh,
changing these data types.
but this is doing what I was talking about. So this, if I understand you right, this looks through every cell in the simulation, and it asks, does it have the rule type switch request? Is that right?
Yeah, like this has been stored in the dictionary.
Okay, so type switch request, though, no, type switch request is a trigger, right? Type switch request is true when there is a type switch.
Yeah. Um,
So, okay. So, and new type is written by your other. No, but where is the evaluation of the JSON, the thing specified in the JSON file done?
Oh, this is for
There has to be
okay,
something that reads the JSON file and does something with it. Where is that?
Lord. We just
Okay, there, maybe.
okay. So this
There you go. Load rules. That looks like it. Can you make that bigger though? Can you pull it? Can you pull the right-hand side over to the, so there, thank you. Because there's a lot on that slide, so I want to make sure I can see it. Oops. Okay, I get that
to
right. Okay, so you load.
load the rules from the JSON
Oh, just
file.
hold on. Let me slow. I'm sorry, I'm not as fast as you are, sir. And it's small,
I'm
so I
sorry,
have
my
to.
bad, my bad.
No, no, not at all. So you read the rules for the JSON file in line 31. Okay. Now you step through each rule in line 35.
Yeah, and I get the target ID, which is the cell ID.
Is the cell, well, you said before it was the cell type. Is it the cell type or is it the individual cell?
The target ID is cell type. I
Okay.
didn't like
I wouldn't use the word ID for that because in CompuCell at least ID really means that's the
all
individual
specific
cell.
individual cell.
Yeah.
Yeah. Okay. So,
Target type would be fine, but target ID
okay.
would be the individuals. And you might want to have both. In other words, you might have a rule that only applies to one object as
Yeah, that's
opposed to
true.
a class of object. But that's fine. But for the beginning with the class is fine. Oh, okay,
Yeah.
fine. So you pick the at okay, so you find the target, okay. Then you iterate
Um.
over all cells of that type. Yes, okay. And then you look at the cases of the rule. Okay.
Condition. Behavior type.
So self dot behavior registry get behavior is the thing that actually evaluates the output of the rule. Where's the rule evaluated?
Rule evaluate. Oh, that
Where does the rule actually read, say, the chemical field concentration?
here. Model registry. I'm not sure if I understand the rule.
Well,
Here
the rule
or like
takes
separate.
some input and gives you some output. Where does it do that? Where is
Um.
the value of the rule evaluated? There must be a
I.
function that does that.
Um.
Pedro, help me out because I'm obviously not being clear.
Question.
Can you hear me, Pedro?
Yes.
I
This
mean, at some
applies
point
to.
you have something that says there's a hill function. You must read the input, the x-axis of the hill function, and evaluate what the y-axis is. Where do you do that?
Oh, I see. So this is for model registry,
Right.
and you see like um model registry. Wait, behavior registry.
So the way I will go about finding that is if you go to your steppables where you use the heal function, look at the
Is
way
it
it's defined.
hmm,
Here,
isn't
right
that
here.
apply? Is it a function that
Okay.
function called apply rule?
Yeah, so model registry. So go to model registry.
This one, this is a um. I
Yeah,
mean,
you have
uh,
from model
yeah,
registry. So
yeah.
go to
Like
the file model registry
no, the model registry is right here.
there. Yeah, okay.
So it's yeah. So this includes it's a dictionary including three
Types of
functions
model.
here.
Yeah. Okay,
Yeah,
fine.
and the functions are defined here upward.
Wait. You're going
Oh,
way
okay,
too fast. Much too
okay, okay,
fast.
okay. So for example, this is the expression model, and it'll just
So
get
here you
the
read the
attribute.
field
Yeah, and yeah, it
and you,
identifies the center of
right. So now
mass.
you put it into now you're reading the value of the field. It's in local var's name. Okay. And so somewhere, so it's eval, it's line 69, huh? Or is it, it's actually, no, sorry, it's actually it's 53, right? The function is expression model, is that right?
Yes.
Yeah, like there are three numerical models. For example, this is the Hill model, and these functions are stored in the dictionary.
Right.
Yeah, and in the stepable, you just need to identify which model you're going to use
Yeah.
Okay.
in that case. Yeah.
So where is Hill model called?
43. Okay. No.
Our Hill model, it's here, and
Yeah,
No,
it's
no,
going
but
to
this
use
is
one of these functions.
somewhere else is going to call that, right?
yeah, so you just
Yes,
go back to the stepable. For example, this is
right there.
growth
Yes.
stepable, and by get this method for a dictionary, you just get the
Right.
value of the corresponding key.
Okay, so it's in line 21, you're applying the model.
Yeah,
Model underscore FN is actually evaluating the model line.
yeah,
Okay. So basically what would change is that instead of having line 21 be delta equals, you'd have cell dot dict quote something equals. And then you'd have to have some separate thing that if it happens to be the volume, you set cell dot dict delta volume, cell dot target volume plus equals delta cell dot dict delta volume, something like that, right? So Pedro, is that your idea?
Yes. Yes, model fn, if your model name is a hill function that returns a
A
hill
number.
function output. Yes, it returns a number. Yes.
And so instead of returning delta and making it specifically the target volume, it would return some dictionary entry where the model FN also knew what the name of that key of that dictionary was for the output.
Yes.
Yeah, okay. So I don't think that would change what you're doing very much.
I could just make some modifications on that.
I mean, is it clear what you want to do? So in your case, you'd have one extra thing. In other words, line 21, instead of returning delta for cell dot target volume, would return cell dot dict quote delta volume. And then you'd have a line that is line 22. It says cell dot target volume plus equals cell dot dict delta volume. And in that case, modeled underscore FN would have as one of its arguments the key that was being modified on the output, right? It would have the name of the key that of the dictionary key that was being modified. And I think that makes things more general. You could still have all the code you have here, and it's not going to change anything except the left-hand side of line 21.
Yeah. I think yeah, I'm getting your points. Because before probably I like my awareness, my knowledge didn't get there, so
No, this is very impressive. I'm not trying to be difficult. Uh, and if you hadn't shown this, I'm not sure we would have thought about these issues the way we are. So
okay.
I don't want to make it sound like you've done something that isn't interesting and correct, it clearly works. The issue for us, and something that Herbert Sauer talks about a lot, is that you want to make sure that when the code base changes, your software doesn't need to be changed. So the interface between your rule language and the software may need changing, but you don't want the rule language interpreter itself to change, if that makes sense.
Yeah, that makes sense. Thank you.
So,
Thank you for
but
so
I'm extremely impressed with what you have here.
thank you.
It's a lot. And I would really at this point try to meet as soon as possible with Pedro, try to get Maciek or Peter on it. I don't know about TJ's availability. And walk through it, because I think Maciek will be very pleased to see this.
But probably give me
And
some time.
he might have some technical suggestions about way to make it cleaner or faster or these kinds of things. But in general, I think he's going to be very impressed by what you have.
Thank you.
I think the changes he would make would be fairly small. And as I say, the change that we're suggesting, which is always assume you're going to, as an output, to a dictionary entry, doesn't really change much. Actually makes your life a little easier.
Okay.
Okay. Pedro, do you have any other comments at this point? And again, I'm not an expert in these things, so I'm not necessarily the best person to advise you, but that's how I would respond to what I see.
I think this is going to be hard, honestly.
What?
Um, like shifting from creating new modules to just doing parameter updates using her framework. Is that where we're going to, or are we sticking to creating behavior modules, new behavior modules?
Well, I don't have a problem creating a new behavior. So is every rule affecting cell growth going to be its own steppable, or are all growth related rules going into one steppable?
So now it's going to all different steppables.
So basically every line in your rule grammar creates a new steppable.
Yeah.
Well, in terms of modularity, that's probably the thing that you want. I think my concern is it's going to be very slow when you put it in Python that way. Again,
Yeah.
if you look at the way Vivarium does things, that's how it does it. Spins up a new instance every time there's a new set of relationships. But it's all hard code. I mean, it's all compiled, so it's not.
Okay. So
I would have thought Vivarium would be cumbersome. It would be too slow to work, but it does work. But in terms of the issue of how do you aggregate things, and do you spin up a new steppable or a new class, or try to have things shared? I mean, with Pedro, with our network models, right? We spin up a new instance of libRoadrunner for every network in every cell. I think the only question here is how much overhead there is. There's overhead the first time you instantiate the class. I mean, the steppable. Once it's loaded, I don't know. I mean, running through, you have to run through every step of bull. In terms of modularity, it's the right decision. In terms of execution speed, I don't know. And that's why I would talk to somebody like Maciek, who's a hardcore developer on this and who might have more insight into it. Pedro, are you comfortable writing to Maciek, or do you want me to do it?
I can write to him. Can schedule a meeting for well, I don't know his availability though.
That's what I'd say. I think Xiaoyu may be available over the weekend too. So I would,
Yes.
Maciek usually is only available on weekends. So you might be able, I'm going to be away this weekend, but you might be able to get a meeting with him this weekend.
Yeah, I think this weekend works for me.
Right, I'll send an email.
Thank you.
I'm writing the email. I don't know if you want to do it, James.
You can put it. Why don't you just show me why don't you show me what you're planning to send? But I think I think it's impressive. I think you've done a lot of work. You've gotten much further than I thought you would by this time. So yeah. Yeah. Right. I mean, I would have not just made great progress, she has it working. Right? It's not just fantasy, it works. Um, are you available this weekend for talk? That's fine. I might send it. Well, I was gonna say I'd send it to Pete,
What did I
to,
do?
who deleted your.
Oh,
It's in
right.
drafts. All right. I might send it to Pete too.
Peach.
Yeah.
Good enough?
Yeah, sure. So that's fine.
All right.
No, that's a lot. There are a lot of different ways of doing this, and the philosophy, it's not that there's a single right or wrong way to do it. There are a lot of different philosophies about how to organize this. And so, um, but I do think of Herbert, and Herbert is a strong believer in exchange languages. So you take antimony and then it produces an intermediate language, and then each solver has to do its own parsing of that intermediate language. But that way, when people change the solvers, they're responsible for changing the interface to their solver. But the base language and its code generation don't change. So they try to separate the user interface and the model specification from the implementation in the particular environment. So Great.
So should I just end up sharing and
I mean, we can talk more if you like, but I think you've already shown me a lot. Um, and I apologize. I don't know how much more, I don't know how long this class is going to be because I'm very tired today.
oh,
I was in,
y-
I'm happy. Let's do a little bit of a lecture, but it doesn't, but I may not do a full 3 hours because, uh, I was in,
it's, yeah,
I
it's
was in
definitely
Monday morning. I left very, very early from Indianapolis to go to California. And then I worked all day Monday with graduate students at University of California, Riverside. And then Tuesday I worked with the junior professors there. And then I gave a colloquium. Then I went out for dinner with the senior professors. And then Wednesday I flew home. I didn't land in Indianapolis till 11 o'clock last night. So I didn't get home till 1:30 till 12:30 this morning. So I'm a little sleepy. But
yeah,
it was very
relaxing.
nice. It was a very nice trip. And the 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 solver engine that Mark Chaplin Mark Alber has developed is really powerful.
Albert?
It puts Physicell and Tissue Forge. Well, I shouldn't say it puts them to shame. Let's just say it's very competitive with Tissue Forge and CompuCell. Not CompuCell, Physicell. Uh, it's fully GPU structured, and it lets you build center models, finite element mechanical models, vertex models, subcellular element models, and it has a full fluid dynamics solver. It has a full Navier-Stokes solver in it. Um, and it can handle hundreds of thousands of particles. So it's quite impressive. It allows them to do detailed cell morphologies, fibers, so they can do extracellular matrix remodeling. It's really impressive what they've got. But but the models are all hard coded. So you have to redo the CUDA to the back end solvers are modular, but the actual model specification has to be written in CUDA as well. And so it's not so convenient to change the models. It's a little bit like the old version of Physicell, right? Where you had to write C++ to do it.
Yes.
But looking at the simulations that he's got, they're really impressive. They're much more detailed than you could do with Physicell or CompuCell at this point. And so it was quite interesting to see what they have. And they use it for a lot of different problems. It's not even though even though the model specification is a little more complex, they still use it for the solvers themselves are very, very powerful. And so they use it for a lot of purposes. I think it's the kind of thing where if you could put a front end to make it scriptable, I mean, he really would benefit from having that Physicell Studio as a front end for his code, for example, because the back end is amazing. It does a lot of things that Physicell and Tissue Forge and CompuCell don't do. It's got a lot more features and it's a lot faster. So, and it's
So
been,
with
I mean,
so with its algorithm, so or it's just because it's more um I mean it gets stronger in computing, so it's just computing the physics, mechanics thing so that it could get better results or it's just
well,
it has
well,
an
it
advanced algorithm.
it has a lot more features. Physicell is fairly limited in what properties the cells can have.
Oh, I see.
So the cells, the point particles intrinsically have polarization vectors and planar polarity vectors. You can define clusters easily. You can define links between components easily. You can define breaking and link forming rules easily, which Tissue Forge is very good at. Um,
I see. Thank
but
you.
I mean, I think it's possible to do everything. It would be possible to do everything that he does in any of these. I mean, in principle, any center model can do any of these things. It's more a question of how convenient it is to do it and also how fast it runs. And so I think the issue is that he's defined more more processes and more object types as primitive concepts than we have in these other frameworks. Also, Dirk finally has released his incredibly sophisticated center model code. Dirk Drezdo finally, after 20 years, has released his center model code. And that is very powerful. Um, and so for me, one of my frustrations is everyone goes out and writes their own solvers. And if people work together to build, to improve a couple of them instead of writing a new one every time. But also, it would be nice to be able to take modules like your rule set module and run it in all of these different frameworks, which I think is another reason to try to separate a little bit the rule interpretation from the specific details of CompuCell. So didn't I sent you a link, Pedro, didn't I send you a link to the fiber model that Mark had this morning? I
I don't
thought
think
I had
so.
emailed. No?
No.
Well, I think maybe you're right. Maybe I sent it to Michael Getz because he's been working on fiber models. But let me see. I can send it to you guys. Oh, let's see. Yeah, let me forward this to you. Okay, I sent you a link to some of the papers, just so you can take a look at how they do it. And they're not, this is back end things. It's not how to do rule sets. Okay.
But that's interesting to know that. Thank you.
Yeah. Well, I guess I was familiar with, I mean, I knew some of the work, but I'd never been walked through how they did it in detail. So I didn't perhaps appreciate enough how much they had achieved until I saw there. So went visit. All right.
Is this a molecular dynamics simulator plus a fiber thing? How is it?
Well, it's a particle model, if you want to call that MD. but it has the idea of bonded interactions that Physicell didn't have, at least, or it didn't used to have, that
Hmm.
Tissue Forge has
Right.
natively. And so,
So they
so
can create nets.
that's right.
Yeah, that's very
So,
nice.
so it's more of a solids modeling package, right? It's more of a solids modeling package. It's a finite element solids modeling
Yeah.
package.
Sometimes in my free time, I think about modeling hair for some
They
reason.
do model hair.
Yeah, that's very cool. I'm
And
interested in that.
actually, their hair model is one I would like to see replicated in CompuCell.
Oof.
No, because the model, well, I mean, they don't model all aspects of hair, but they're modeling hair growth and loss. So that they have a detailed model of the
Hmm.
follicle, and
Oh, okay.
the follicle goes through cycles of growth and regression. And
Ah,
it would be expensive in CompuCell
yeah.
because it's got a lot of cellular components, and you'd have to cross-link everything with links. But I think you could do it. I think you could, in fact, implement exactly their model in CompuCell. I know you could do it in TissueForge pretty easily. Something that's nice in their model, and I don't want to take too much time from Xiaoyu, is you get these flows, counter flows, and
Mhm.
we often have trouble creating a basement membrane or something like that. So the way they work is they have two cell types. If the cell types are in contact with each other, they generate a layer of small cells between them, a lubricating layer. The
Mhm.
lubricating cells generate links transverse to make that layer rigid. And then the two cell types above and below it don't bind strongly to that layer. So you have a lubrication layer, and then you can have the top layer move to the left and the bottom layer move to the right, which you see in development all the time. You see these counter moving flows that are right next to each other. CompuCell doesn't do that naturally because things stick together in CompuCell. And so it's hard to get that to work. I think Physicell could probably do it. Well, I don't know. You have to have links, but if you had links, you could do it. It's a case where center models are easier to make it work. So
Okay.
anyway, so we'll get to links. We should probably do links the week after break, right? Better.
Yeah, so we're
All
going
right.
to have spring.
Okay. I mean, the choices are normally, I mean, normally the next thing I would do would be normally the next thing I would do after this would be network models, but in a sense, I think you know how to do the network models pretty well already. And so maybe doing links and the mechanics of them would be, think about it. I can do either one. So today I wanted to, in our remaining time, I wanted to come back. I'd asked you to work on that little angiogenesis and vasculogenesis simulation. Sorry, I have the angiogenesis, vasculogenesis. That's from last time. I'd asked you to work on the bacterium macrophage simulation a little bit as a homework problem from 2 weeks ago. And I wanted to see how that went. And if you we could do it in class a little bit, or you could just show me what you got. And then I wanted to jump into the persistent cell movement. And Pedro is really the expert on this, so he may wind up having to give some of the lecture. He wrote the slides. So, but let's talk about that. In a sense, the persistent cell movement is how Physicell does cell movement. And in CompuCell, it was something we had to add to it. In Physicell, it's a native concept. So we'll come back to that. So both in class and in the homework, we looked at the angiogenesis, this very simple angiogenesis simulation, and thought about how the model structures we picked affected whether you got vascular patterns or blobs, and also what controlled the size of the domains and also the thickness of the struts reorganization. And then at the very end last week, and then in the homework, we had this chemotaxis example, and that was inspired by this wonderful movie from the 1950s of macrophage chasing a bacterium. And the goal was to build a simulation that looked pretty much like that. And this is a fairly well-developed simulation where we have the blue cells are behaving like the macrophages, the green cells are the bacteria, the red cells are the red blood cells, and we see the macrophages chasing the bacteria. They don't eat the bacteria because that's a separate mechanism which we don't have included. Physicell actually has a concept of phagocytosis, so in Physicell that's a concept. In CompuCell we have to, what you'd have to do if you wanted to have that really eat the bacterium would be to have some rule of engulfment by adhesion, and then you'd have to essentially change the identity of that cell to be the same as the blue cell, and then that would then change the target volume so that the volumes are conserved. So you have to do that by hand. Something you'll notice in the simulation, it's got periodic boundary conditions. The other thing that you may notice if you look carefully is that it's on a hexagonal lattice. And we haven't talked about square versus hexagonal lattices so far, but when you define the cell lattice, there's a tag that you can use to make it hexagonal rather than square. And actually, a lot of the problems that you see in terms of cells freezing or lining up with the lattice or lattice symmetry axes are much less severe in hexagonal lattice. So it's often interesting to switch to the hex lattice. There are a couple of little things that can be complicated in hex lattices, and a few of the plugins don't work very well in hex lattices, but most things work. Volume, surface, these all work in hex. Yeah, shoot. So I don't know why there's this bad sound associated with this movie, but again, the first thing we're doing is trying to make a set of biological observations about what we're seeing. We see the bacterium, it's small, it's compact. It's not clear if the bacterium is moving actively, if it's just being pushed by the larger cell. And because we do not have hydrodynamics in this model, if we want the bacterium to actually move away from the macrophage, then we have to include some kind of repulsive chemical field to do that. Because in reality, fluid is advected by the cell and that pushes, but we don't have that fluid to do the advecting. The neutrophil is fairly floppy. It's got a fairly large surface to volume ratio. It sees the bacterium from a long distance, which means it's responding to a long-range chemical field. And it moves actively in the direction of the bacterium and eventually eats it. And when it's moving, the velocity is fairly constant, which suggests we have a logarithmic chemotaxis, adaptive chemotaxis. And the red blood cells don't do much. They just sit there. And they're fairly round, so they have a small surface to volume ratio. And nothing sticks. None of the cells stick to the other cells. And so one question that is a little hard to determine from the pictures is, but you have to answer for the model, is does the secreted signal from the bacterium diffuse around or through the erythrocytes? And what would be different? And that's something you can do very easily in the simulation. You can add a tag, do not diffuse, to the cell type erythrocyte. And in that case, you can explore what the difference in the cell movement is. So at the level of a conceptual model, we're making a biological hypothesis. The neutrophil is chemotaxing towards the chemical secreted by the bacterium. So we have three object classes. We have the bacterium, the neutrophil, and the erythrocyte. And to begin with, we just have one chemoattractant chemical field. And the simple movie that we have here, there's one bacterium, one neutrophil, and multiple erythrocytes. We can change that. If we had a movie which had, it looks like we maybe have two bacteria in the movie. If we had a movie that had multiple erythrocytes or multiple bacteria, then the way they interacted with each other would tell us about the diffusion range of the chemical and those kind of things, but we don't have that movie here. There. Better. So now we have to define properties for our cells. Well, they all have a volume, they all have a surface area. The bacterium may not actually have any active motility. They all have contact energy or adhesivity. They at least don't stick to each other. We don't see any cell division or cell death in the process. And we have this one chemical field that diffuses and decays. And what are the interactions? Well, the bacterium secretes this bacterial chemoattractant. Your neutrophil chemotaxis towards the bacterial chemoattractant. We don't know whether it eliminates the chemical signal or not when it responds to it. And we don't know whether the chemoattractant diffuses in the red blood cells. And so what are the parameters that we have to specify in our model? Well, we clearly have to specify the volume and target volume and lambda volume, target surface, lambda surface for all the cells. And the bigger lambda volume and lambda surface are, the less movable the cells will be. We're going to have to define a secretion rate for the bacterial chemical. We'll have to define a diffusion and decay rate for the chemical. We'll have to determine whether the neutrophil absorbs the chemical or not. If it does, how fast, how much. If the chemoattractant diffuses in the red blood cells, we have to say whether it does or not. And we have to define the contact energies to say that they don't want to adhere to each other. And so that was the basic assignment. I think it was a homework assignment. Did you do that homework assignment yet?
Oh, um, I'm
Go
sorry,
ahead.
can you hear me? I didn't do it yet.
Well, so why don't we try it here in class?
Okay.
What I would do is I wouldn't do it from scratch because it takes so too long. But in the demos folder, there is a bacterium macrophage or bacterium neutrophil. I don't remember what it's called now, but there's a version of the simulation. So why don't you why don't you open it, find it and open it, and first open it and twit it and then in player, and then run it and see what it does. And if you can't find it, let us know and we'll
Oh, sorry, but do you mean like download it from the Google Drive or the because which is
It's a built-in demo in CompuCell. It's in the demos folder.
oh okay. I I
I-
didn't open that file before, so
Pedro, can you find out where in the demos folder it is? Because I don't. The demos folder keeps getting reorganized. So
I think it's in a folder called Book Chapter Demos.
for me, the demos are organized in the most obscure possible way.
Yeah. There's a
It,
bacterium macrophage,
macrophage.
steering, 2D steering. Um, there is models, demos models. There are other ones. Um, yeah, I think it's this bacterium macrophage periodic inside models.
Yeah,
There's a
because we
folder.
don't want steering because that's all sorts of extra detail.
Yeah.
so in my demos directory, I think the
Models.
close
Demos,
models.
models.
Oh, okay, models and no steering, so it's periodic.
Mhm.
Okay, thank you. Oh, it looks okay. Yep, like there's yeah, I think like the initial version looks okay.
So do you want to screen share it? So
Oh,
before you do that, you
mm.
run it a few times. Does it start out with a single bacterium?
No, we start with 4 bacterium.
So the instructions are to change the code so you only have one.
Okay,
And then you want to make sure that the neutrophil finds and follows the bacterium. And you're going to find that you're going to need to make it work properly, you're going to need to have use the logarithmic chemotaxis. If you use the linear chemotaxis, it won't work, or it won't work very well.
so uh, can I screen share this because the initializer is a PIF initializer, and so I I have no idea like how to change the initialized number, initial number, and
Okay, well, we haven't done PIFs. PIF is a very old format for specifying the layout of cells. So if you go into so one thing you don't want to do, so save this project somewhere locally because you don't want to clobber the demo. Yeah.
right, um, just
You never want to edit the master copy. Okay. All right.
right, this one.
All right.
Mhm.
So if you open the PIF, which is there on the left,
This
see the
one.
PIF, double click on that. Open that.
Um, I double click that, but
It should is the tab. There should be a tab for it. I have to look. Can't see your
oh,
screen.
okay.
There it is. It's pretty easy. It just You literally list each cell individually and the voxels belonging to the cell.
Let's see. So
And
that
so
means
where
modify these.
right. So where you have the bacterium, you could just you can comment out the extra bacteria.
So how do you use like hashtag for comment ellipsis file?
Well,
Comment out.
just delete those lines. It's
Oh,
easy.
okay. Um, so the first, and we have like two to go. Oh, here.
Well, I would probably delete the ones later down. I keep number one and get rid of the
Okay,
higher numbered ones.
okay. This. Oh, there's a zero, but that doesn't matter. Okay.
I'm sort of surprised the zero works, but anyway.
Okay, so yeah, I think here it's let's set it down and
I mean, try making a few changes and see if it still runs, and then you can keep modifying it.
see. Oh, there's still like, did I save that? I saved that, I think. But you can see
You're
there are
probably,
still,
are you running this? Did you reopen this one? Or are you running the other?
just reopen it, making sure. I crashed. Wait, is it crashed?
Can't tell.
Oh, here it's here.
Excuse me, I'm gonna get some water.
Still like three.
If you go through the PIF, you should try making just one, get rid of all the bacteria except one.
One.
I think you got rid of. Oh no, there's one there. Yeah, there is
Yeah,
one. Yeah.
thank you. Let's see. Bacteria. Yeah, I think that's the only bacteria here. Thank you. Did it say that we need to change the diffusion field? Like, it's not like linearly distributed, but logarithmically distributed
The diffusion view,
field.
the field
Uh-huh. This is
to
like to change the chemotaxis from this log.
logarithmic.
Yeah.
Yes. Yeah, and we do that in Python.
Oh, okay, okay.
So if you go to, I don't know if, yeah, let's go to CC3D project.
Mm-hmm.
Oh, wait, no.
Python.
C3, yeah, Python, and then cell attributes.
Uh-huh.
Uh, cell constraints, one below. Chemotaxis. Chemotaxis. By cell ID modifier, let's try that. Never click this one. Modify. Delete this.
All of this.
Yeah. Go back to CC3D Python. chemotaxis the modify options. This one. Yeah, so cd dot get lambda and cd equals this chemotaxis plugin get chemotaxis. That's how you modify the lambda chemotaxis. And then here you
Oh.
can choose a function of your liking. So you can do logarithmic chemotaxis from here.
Oh, okay. So it's kind of like linearly changed. So,
Oh, you're not going to do it automatically. You want to do the calculation by hand?
oh, because you're going to like, you're going to change the chemotaxis. Um, yeah, chemotaxis are not in the from a linearly distributed way to a logarithmic way. So you're
Well,
going to
when
do it in Python.
in the XML, you can specify the logarithmic chemotaxis.
Oh, okay. But
I
yeah,
mean,
okay.
there's no problem. It's probably better to do it in the Python, but I just wanted to say you can do the logarithmic chemotaxis.
Okay. So just so how do you do that?
So I recommend using the manuals.
Okay.
So so I think it's the log saturation coefficient is the term you need, but we'll have to look it up. Why don't you just go to the CompuCell manual website?
Yeah,
You
go
should.
to the website, check the manual, but I think I know what's going to happen. The saturation is not equated the way we want.
And if we find mistakes in the manuals, please report them.
Access. That's not right. Um,
That's the Pythonic one.
oh,
So
okay.
go
Yeah.
to Chemotaxis plugin. It was on that page. Just there was a link to it on that page. Just go back to the one you were at. Go back to
Okay.
Chemotaxis on where you were.
Oh, um,
You must slow down. Go back to the page you were on, which said chemotaxis on a cell by cell basis. That's fine.
okay.
Related chemotaxis plugin. Click on that.
Oh, okay.
There. So this is how to do it in Python. Chemotaxis data set log scaled coefficient. If you want to do it in Python. Now, if you want to do it in XML, you have to look at the other manual, unfortunately, because this is probably let's see where the XML manual is. But anyway, that's where the Python spec is. So we need to go to the XML spec.
So not this one?
There you
Oh,
are. No, well, this is showing how to undo you need to look at the manual for the XML.
oh,
Well, here, it is there. It is there. Don't just
okay. Is there saturations coefficient?
right. But the regular saturation coefficient isn't the one we want. So let's see if it has it here.
Okay.
Saturation
Linear.
linear. We want the log saturation coefficient.
Okay, I see.
There
Here.
we go. Log scale coefficient. That's the one you want.
Okay. Mm, medium.
And you can tell what the example that the code was pulled from is because it says bacterium and macrophage in the example.
Yup, so this. So that means from medium to bacterium, huh? Or should I like switch the position of the two objects?
No, that doesn't do anything.
Okay.
No,
Oh,
so it's important that when I assign reading for you, it is important to do it. Because I had asked you to look this up. And it's fine. We don't all have, we all run into things where we don't have enough time, but this is an example of something where, so
Oh, okay.
when you have chemotaxis by type,
Mm,
you, the syntax here is a little bit backwards, although I think you can have these in any order. The thing that is doing the chemotaxis is all the way at the right end. Type equals macrophage.
okay.
Okay. Oh, Pedro, can you please explain? Somebody's ringing my doorbell. Hold on.
Okay. What is it that I need to explain?
What like the right? So like the order of these two laws.
Oh, okay. So chemotaxis towards is what you allow your cell to move to. So chemotaxis, and let me, oh, I cannot draw. This is annoying. So you have your cell and there is a field. The chemotaxis in CompuCell will copy the cell pixels in the direction of the gradient.
Mm-hmm.
Okay, so it do pixel copies in the direction of the gradient. But when you do pixel copies, you have to check what is the cell that I'm copying to, because the cell is copying the pixel, and then the pixel that is being converted to cell could be medium, and could be something else, could be another cell. So if you set chemotaxis towards something, you are basically restricting the medium where your cell can perform chemotaxis to. So for example, if you set chemotaxis towards medium only, then your cell in question here is macrophage, type equals macrophage. So your macrophage can only perform chemotaxis towards a medium. So the target copy has to be a medium pixel.
Okay, I see. So like these are the like passive objects that
Yeah.
receive the chemotaxis from. Okay, okay, I see. Oh, I just thought of a stupid question.
Uh, I wish I could draw because it's much clearer to see drawing. But imagine
Uh,
like you have macrophage migrating, and then macrophage is going to like to the right, and then it collides with a bacterium cell. The way you have here chemotaxis towards the bacterium, the macrophage will push the bacterium as it performs chemotaxis because you allow macrophage to copy pixels towards bacterium cells. If you remove bacterium from this list, then once macrophage encounters a bacterium, collides with a bacterium, it does not push the bacterium to the direction of migration. Bacterium will basically inhibit the migration of macrophage.
I see.
Then lambda is the intensity of the force. So if you increase the lambda, basically your cells will move faster. And the log scaled coefficient, that is a parameter that, to understand what that does, you have to check the formula in the...
But the main thing is that it means that normally the problem with linear chemotaxis, which we played with a few weeks ago, is that with linear chemotaxis, if the chemical field is very small, you don't move. And if the chemical field is very big, you move too fast. Well, if the gradient is
Oh,
too small and too fast. With
yeah.
the logarithmic chemotaxis, the macrophage can see the bacterium even if it's quite far away. Otherwise, the macrophage won't see the bacterium until it's right next to it, practically. And so that's the reason for the log scaling.
I'll just delete.
Now, you don't need the chemotax towards at all. If you didn't have chemotax towards at all, the problem is that you chemotax towards the the red blood cells, and you don't want that. So you'll find out that that wouldn't work either. But the question was really to try to explore all of these options. There are many decisions to make.
Okay.
And these are really biological decisions. How does the cell respond to these particular situations? They're not really computational decisions. They're really about the model structure. But yeah, this is fine. You could try. I just comment out that first one because you may want to put it back. You may want to use it again.
Let me just check. Finish.
Edit.
No, I just wanted like to see how to comment out the XML.
Just go to edit,
Oh, edit.
edit,
Oh, okay. Oh, I see.
and hit comment.
Oh,
There.
thank you. Okay.
That should
So
work.
okay. Mm,
I don't like. I wish we could set the colors of cells in the XML, Pedro. It can't be that hard to do that.
I really would love that, especially because when we write pure Python scripts, there is no way you can change it.
Why don't you please ask Maciek to do it? It's about 5 lines of code, but it has to get put into the parser and then also into player.
Yeah. I'll send him an email.
Basically, what has to happen is the XML has to get turned into the JSON for the player. Anyway, it ChatGPT thinks that feature exists, by the way.
what feature? So you mean like you
When
can
you say
modify?
cell type, that you can define the color of the cell type. ChatGPT is convinced that you could do that
That's how to make it
because
easy.
you should be able to do it.
Yep.
But anyway, okay, so this is getting closer. Okay. Now there's some things, let's just run it and see what it does.
Mm-hmm.
I don't see the macrophages but responding to the bacterium very much.
Let's see the wait. Cell is not defined.
Did it crash?
And after running after running around 10,000 Monte Carlo steps in code.
Okay, so something interesting happened because if you look at the code error, there's actually a typo in the XML in the Python. So let's look at the Python.
Oh yeah, that's because we just add some comments. Some comments.
Oh, you
So
put
just
that.
delete
Yeah.
YAML to run it and modify this by Python, but okay, let's just rerun it.
So let's look at the chemical field.
Mm, chemical field, okay.
Mhm. So
So if we look
that's the chemical secreted by the cell,
the micro yeah,
by the macro,
bacteria.
by the bacterium. And you'll notice in this case, it
Well I
looks like
think
we have a do not diffuse in
yeah,
the
cell.
in the erythrocytes. Yeah,
Yeah, and it ends because probably we just allow it
right,
to run
right. So you can
10,000.
change that. So again, the point of this is you start with a model that's not very good, and you learn how to update it to make it more interesting.
Mm-hmm.
Right. Okay. Everything else looks okay for the moment. And you'll notice in line 58, it says that you don't diffuse in the red cells, don't diffuse in the
Yeah.
erythrocytes.
Mm, yeah.
And that's fine. There's no reason that you can't do that. So let's try again.
You wanna like modify some parameters here?
No, let's just run it so it doesn't crash.
Oh, okay.
So do the macrophages respond to the bacterium?
Okay. We need to like go back to.
You can always have two display windows, right?
Oh, yeah. Yeah. Just a
The
sec.
button at the top on the right. There. Okay.
Enlarge. Oh, I have to like manually adjust the windows.
So it doesn't look like the macrophages are responding to the bacterium very much, huh?
Yeah. I
And
chemotaxis.
actually, I think my instruction, well, I said, okay, by neutrophils, I said, keep saying macrophages. Right, neutrophils. Anyway, so what do you think could be responsible for that? What parameter in the model controls that?
You mean like this one didn't respond to the micro,
Why not? What is this? There's only one parameter that matters. What is it?
so that would be like the chemotaxis lambda
Lambda
parameter.
chemo, yeah. So you have to make lambda chemo bigger.
Oh, okay.
And if I remember right, you have to make it a lot bigger, like 1,000. But I may be
Okay.
wrong with that.
Okay, let's try. I think
If
my
you don't know,
experience.
try changing it in factors of 10. So if you start with 1, then try 10, then try 100, then try 1,000, then try 10,000, till you find a range that works, and then make it finer.
I think it's. Uh,
Is there any chemotaxis by the macrophages?
One thing that would help here, James, is to set the field, set the maximum to the according to the secretion rate, because we have no idea if the gradient is enough to trigger anything.
Well, I can't see the values if they're too small. I think it's
They are
actually,
powers of like they are 10 to the minus 3, I think, if I'm seeing correctly.
okay, so let's look at the secretion of the from the back the
10
neutrophil.
to the oh wait, 10 to the 3.
I think it's the opposite. They're too big, not too
Oh yeah.
small.
So they should be chemotaxing.
Yeah. So let's see, why is the macrophage not responding chemotactically? Let's look at that. Let's look at your code. Chemotaxis, ATTR, bacterium lambda 10. Okay, so it's possible that the 10 is still not enough.
yeah, well, let's just tune up this a lot larger to
Okay,
see
yeah,
if
yeah.
the.
Yeah, that's maybe too much. You see, they're breaking because you see, they found it, right?
Yeah, uh, chemotaxis toward it. I, 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 I assume that the cell would like be pushed to this. It would have chemotaxis toward medium and oh macrophage. Yeah, macrophage.
Well, so
Uh,
towards maybe is a funny concept. In
um,
this case, chemotax towards doesn't really do very much.
Oh,
You can get rid of the chemotax towards and see what happens. Is it any different?
oh, oh, okay. I thought like in inverse way because I thought like it's bacterial have chemotaxis to a macrophage. But that doesn't make sense. And
No, if you
Pedro just
look at that line, look at line 48.
hmm
The cell that is doing the chemotaxing is macrophage.
yeah, yeah. So
And
macrophage would chase that.
uh, if you
Yeah.
eliminated the chemotax towards command, it would do almost nothing. It'll behave almost the same way. Won't make a difference. The only thing that does is it says that if you're touching a red blood cell, you don't move in that direction.
Yeah, yeah. Pedro just explained this line to me. So
Okay. But
okay.
the lambda chemo is too big here.
Okay, so let's try
Try
100.
100. Yeah.
It's still like
Right. Now there are a couple of other things that aren't really very realistic here. One of them is that the red blood cells are not round enough and are fluctuating too much because they don't really fluctuate at all. And the other one is that the yellow, the macrophage cell, is too square and is also, see, it's lining up with the boundaries, which shouldn't do it. So probably the macrophage medium contact energy is too high.
so okay,
So if you make lambda volume for red bigger,
maybe like 60. Um,
well, that's a pretty sensitive parameter. So yeah, going by factors of 2 is not a bad idea.
okay, and for macrophage, the lambda, I'll say maybe 5. Let's try
Well,
this.
you'll see what happens. I think that may not do what you want, but try it. I mean, only you're not going to break anything. One thing though I do recommend
Hmm.
is that instead of directly editing the code, you remember whenever you run it, it saves a copy. So if you forgot what code you had, you can go back and look it up because every simulation saves a copy of the code you ran. But I like to, when I'm going to do this kind of editing, I like to save a copy of the line in a comment.
Oh, okay.
And then so I remember, gee, I forgot what I had before. So you could get back to it. Yeah, like that. Yeah. So see how that changes. Still better.
But yeah, you're right. Like I don't see. I think like the macrophage cell is still pretty round.
Yeah, so to make them less round, what do? You increase the surface area compared to the volume, right?
Include the surface. Yeah. Along the surface.
Yeah,
I'll just.
that's going to be big, but all right, try it.
Oh, that's for macrophage. Yeah.
That's
And
right. That's what you want.
yeah, but for along the surface. Yeah, I think like we want the surface to be rigidly.
Not for the macrophage. The macrophages fluctuate a lot.
Yeah, I mean like the so the surface is like set to be around 100.
Well,
Wait,
try it, see what happens. You doubled the target surface, see what happens.
yeah, because I set it pretty large, so I don't want it to shrink. Uh, okay, so
That's
I
a little
think
too far.
yeah, it isn't like elongated. Probably we should allow this to be like elongated.
Well, is it behaving properly? What's happened to those cells? Look at the yellow cells. Are they looking the way one would like them to look?
I think it's pretty close actually, but just
You
the
you have
boundaries.
individual pixels coming off of the cell, separating.
Yeah, so that is not pretty um real.
When
Like
does that happen? Why does that happen?
pixel.
What's the condition for which that happens?
Is the contact energy?
Sorry?
Uh, no, I just like,
Well, was it doing it before?
um, you mean like for the microphage?
3 minutes ago, was it doing that?
What? I'm sorry, I didn't quite get the idea.
You changed one thing. What did you change?
Q Texas?
No. What did you just change a minute ago?
Oh, I changed the like lambda volume.
No. What did you change just now?
I changed the target volume.
No. What did you change last?
Target surface.
Right. You made it twice as big,
Yeah.
and now the cell is falling apart. So it means you changed it too much.
Okay. I'm
So,
already like it's
so try 80. That's fine. Try 80 instead of 100. Okay, Pedro,
it's
good
already
night.
80. Oh,
Okay, it was 80 there.
thank
So
you. Yeah,
run
it's
it
already
again.
80.
Run it again.
Okay. Yeah, it's already like 80.
It's okay, so you'll have to make it smaller. 60.
Okay.
That looks better. Still a little bit. The chemotaxis still seems to be a bit strong, but this is not bad. It's better. All right. Now, if you want the red blood cells to be
Oh,
less mobile, you can make lambda for the red blood cells, you can make lambda volume bigger.
so
And you
this.
could also give the red blood cells a target surface.
Mm, yeah.
The lambda surface there is 0, so you could make that not 0. No, don't change the target
Oh,
surface.
okay. Yeah, I see. I didn't notice the 0. Like 10.
Okay, try that. That's getting a little closer.
Yeah.
All right. So I think from there you could begin to go try to get closer to what we have in the video, on the online video.
Yeah.
I mean I'm sorry, not online, but in the slides. I wanted to just show so that that's the first exercise. And now in my suggestion, I started with only one neutrophil. We didn't do that. We still had multiple ones.
Mm.
And then there are questions, which is if you have multiple bacteria, what happens? That's actually quite interesting to watch. If there are multiple neutrophils, what happens? Well, that you have. If the neutrophil absorbs the chemical field, does it change the results or not? It's pretty easy to change that. In your case, since you're not actually doing an uptake, what you can do is you could say that the chemical decays in the neutrophil. You can define the decay constant in the neutrophil for uptake.
Okay.
And then, as I mentioned, we can't do hydrodynamics, but we could create a short-range chemorepulsion where the neutrophil secretes a chemical, short-range diffusing chemical, and the bacterium is repelled by it. And then there's a question, what diffusion length do you need to match what you see in the movie? Because if you look in the movie, there's a typical distance between the bacterium and the neutrophil that's maintained until it's eaten. And the bacterium itself is about half a micron across. So if the bacteria, if you measure things in units of the bacterial length, then the distance the bacterium stays from the neutrophil is about two or three bacterial cell diameters. So it's about 1 micron, 2 microns. So you need a decay length of about 2 microns for the repulsive field. And then the other thing that's quite interesting is to switch to a hexagonal lattice. So why don't you try that?
Didn't try that before, so is it?
And then the last feature, which is a little bit more work, you have to do it in Python, is make the neutrophil eat the bacterium.
Yeah, but for the hexagonal thing,
Mhm.
yeah,
If you want a screen share, that's fine.
oh, okay. So I've never tried to do with hexagonal lattice
Yeah,
before. So it's like by default it wouldn't show up here, right?
right. So if you don't remember how to do that, again, let's go to
Okay.
the manuals for the moment. Probably the easiest.
Man. Okay. Oh, I'll just use this computer.
So go to the index. And so I think it's common. Let's just write common CC3D. Well, this is the Python tutorial. So you want to be in the reference manual, I think.
Can you like it's a
Just type hexagonal in it's hex in the there you go.
lattice type
There it
lattice
is.
type
You just went past it. There.
hot section. Okay.
Mhm.
So here.
Yeah. Okay.
Oh,
There
I
you go.
think that's closer to what we
Yeah,
saw in
it's
the
not
video.
bad.
Um, but
So again, if you wanted the bacterium to move away from the macrophages, then you'd introduce a second field to have it repelled.
so do I have to do it now, like, or just
Well, I don't know how much longer you want to go. I mean, why don't you try doing this? I think these were all in the homework.
Yeah, I
So I hope now that we've done this together, maybe going through it again and doing it as a homework assignment will be okay. I'm happy to work with you on it. If you're not confident, you can do it.
I think I could do it on my own
Okay.
as homework because just so that way we could just
Right.
pro progress like the
Right.
contents of our lecture. Thank you.
Oh, well, but I understand that. That's why I want to go over the homework with you in class, because if you have something that you don't understand, there's a question. Sometimes you find a mistake in the manual or something's not there. These are all possible. So I want to make sure that we look at it together so that you don't get stuck or frustrated.
Yeah, it's faster, but
So I don't know today, I don't know how much more we're already 2.5 hours into class. I'll introduce this. I don't know how much time we're going to have to do exercises on this. So in a sense, this is a very simple concept, which is we're going to apply an explicit force to a cell. That's it. And for both chemotaxis and explicit force, in Physicell, because it's a center model, there's no ambiguity about where you apply the force. It's always applied to the cell because the cell is a point. In CompuCell, because the cell is an extended object, you can apply a force either to the center of mass of the cell, which would be like Physicell, or you can apply it to the boundary of the cell. Sometimes it doesn't make any difference. Sometimes they're very different in their outcomes. And so I just want to remind you that there's an option there, and you have to explore which one you need, because they give you different results. So, of course, we know that eukaryotic cells move by creating actin leading edges, or filopodia. And those typically have a lifetime for filopodial and melopodia ruffles on the order of 30 seconds. So if you watch a eukaryotic cell, it typically crawls and then changes direction a little bit, and then crawls and changes direction a little bit. Now, there's some cell types like keratinocytes that roll and move in a very straight line. But remember the last time we talked about this idea of persistence length and persistence time. So by default, CompuCell cells move totally randomly. There is no persistence time for them. And so the plugin lambda-vec just applies a fixed force to a cell, a user-defined force. And it would be nice if we could have some predefined forces. In other words, it would be nice to be able to say apply a Gaussian force to it, apply a Poisson force to it, and so on. But at the moment, we don't. You have to do it by hand. And so why don't we do that? We'll create a simulation. And this is actually, this demo exists, but it's not hard to do it. First, remember that the reference manual has a section called External Potential Plugin, where all of this is documented. So let me walk you through what we're going to do, and we'll see whether we get to do the exercise or just talk about it. So we create a cell lattice. We're going to have periodic boundary conditions. We just create one cell. And there are no chemical fields. Well, if we only have one cell, we don't really care about contact. Well, we have to have contact energy. We'll have volume. We need the center of mass plugin. We need cell neighbor plugin. And we include external potential. local flex. I think now it's only always local flex. It used to be there was an option. And this is one where really you always have to do the external potential pretty much by Python. The only time you might do an external potential that is in the XML would be, for example, if you had a gravitational field, so every cell was being pushed downward, then you might do that in XML. But normally the forces on the cell will change, and so you have to be able to adjust them. So then you can't do it in Python. I mean, I can't do it in XML. You have to do it in Python. And again, there's this comment that you can apply the force at this on the center of mass or pixel based. And it's quite different. The results are quite different depending on the choice you make. And this is probably hard to see. This is the code for the external potential in the XML. Plug in name external potential and cell.lambda vec equals 0.5. It just you specify the vector by hand, the x coordinate, the y coordinate, the z coordinate. And you have to give the algorithm, is it pixel based or is it pixel based or is it center of mass based? And then we create a single cell. And here I used volume local flex, so we create in the Python, we initialize the volume of the cell. And then we're going to need to do random numbers because we're going to have to be updating this by hand. And so we typically have NumPy built in now. So we'll use the NumPy random number generator. And that's usually going to be numpy.random.random. You can do NumPy random uniform min max. I think there's actually a NumPy random that'll give you a vector that's the angular random angle, which is convenient. But you have to remember, there are a lot of NumPy random options. I don't remember all of them. I have to look them up. And so here, the easiest way to generate the force is to pick an angle, a random angle, and then use sine and cosine to calculate the vector. Because we need the vector, but what we want is the orientation to be random. And so here, I created an angle, put it in the cell dictionary, 2 pi times the number between 0 and 1 gives me an angle, random angle. And then I evaluate cosine and sine. And then here, I've done something a little bit fancier, which is I'm going to define how long the cell continues to move in a given direction. And so I define an amplitude for the force, pulsive force here, 20. And I define a persistence time, which I've defined as 0.99. We're going to have exponential decay of the persistence. Okay. And now we have to apply that information to the cell. And it's rather awkward. I mean, it's sort of brute force to do it. Cell.lambda vec x is equal to minus cell.dict propulsive force times cell dict direction x. Cell lambda y, same thing. There's no force in z because we're in 2D. And then the cell will move. And again, because cells move from high energy to low energy, there's a minus sign here that we might not expect. We've run into that before, where a bigger number means repulsion rather than attraction. And actually, oops, there's a PowerPoint has failed here on the image. There should be a picture of a cell here, but the PowerPoint's deleted that. PowerPoint occasionally loses images. I don't know why. It's annoying, but it'll erase some images. In any case, this is the basic result, and in this case, the force is minus the gradient of the potential.
I
And
see.
then in this demo, we are going to plot the center of mass versus time and also the cell trajectory. So in one case, we have the x-axis of the plot is time, and the y-axis is, say, x position. In the other one, we actually make the x-axis x and the y-axis y, and we just draw the position of the cell versus time, so we get a trajectory. Right? And when you put that all together, you get something that looks like this. Here, the cell is migrating from the top left to the bottom right. I've got a strong resistant force, but there's some random movement as well. If I made the force less, it would still move top left to bottom right, but it would be more random. And so you can change, and you can look at things like changing the fluctuation amplitude and see what that does. Okay. Now, and this is the code is available here, Lecture 13 demo, single cell persistent movement. It's in the student materials folder. So the next thing that's more interesting is, in that case, we just apply the force and it stays the same all the time. So the cell just moves in again. Now we're going to have the cell forget the direction it's moving. And there's actually quite a simple way to do that. You say that the current angle, and there should be an alpha here. There should be alpha times angle here. The current angle is alpha times angle plus 2 pi random number times 1 minus alpha. And that leads to an exponential loss of the directional memory with a time scale of 1 over alpha. Well, what I said the 1 over alpha, 1 over 1 minus alpha is the way I defined it. And so in this case, what are we doing? We have the angle initially generated here. No, sorry, this one we've, let's see, we're gonna do it. So in this one, the angle is updated by a random number, and the random number is got a cell.dict alpha, so the amplitude of that persistence time. And I was thinking that looked strange because we don't have alpha times angle here. But then I remember that for angular movement, we have modulo arithmetic. 0 and 2 pi are the same. So we don't have to keep the normalization of the angle to be 1. If we were doing this on the vector of the force, the direction, we'd have to actually multiply alpha by the current value. But for this one, we don't. And if you run that one, and there's a demo for this one as well, and here we're going to plot the angle of the cell versus time. What you'll see is this. So here's the angle versus time. You'll notice that it has some persistence, but it wanders. And the cell will move in these it over long times it's a random walk, but over short times it's direction. And if I change that persistence time from alpha equals 1 to alpha equals 0, the persistence time of this pathway will change. So that one is pretty important to do. You also probably want to be able to calculate the instantaneous velocity of the cell. You do that just by comparing the current position to previous position. On a periodic boundary condition, you have to check if the cell crosses the boundary. We had this happen to us the other time. If the cell crosses the boundary, you have to map the cell position to get that right. And actually, I think if you watch the version of this lecture in the CompuCell Summer Workshop that Gilberto gave, I think, if I remember right, he shows how to do the mapping of the angles. I mean, mapping of the position around the edge of the lattice. Or you can ask ChatGPT how to do it. It's a bit tedious to do the periodic boundary conditions. It's not hard, but there are a lot of conditions that you have to check, and it's very easy to get a sign error or something like that, and then it doesn't work. So,
Yeah.
all right. And so when you do that, this is an update rule based on the direction the cell actually, moved. So biologically, we started out by saying the cell is moving in a given direction with a constant directional bias. And then we said that the cell wanders, whatever direction it has, it forgets after some amount of time with exponential loss of memory. And that's also reasonable. In this case, the thing is very similar to that. But instead of asking the question, making the cell move with a random direction, we're doing what really happens more in biology, which is if the cell moves in a given direction, the polarization vector tends to align with the direction that the cell actually moved. Why would that be different biologically from the case of having the cell lose its orientation randomly? Think about a cell migrating.
Yeah.
And the directional force is going to change. And there are two possibilities. In one case, the cell force vector gradually drifts randomly. In the other case, the force vector is adjusted by the direction the cell actually moved. And as we know in the Potts algorithm, the direction of actual movement is random. Why is it different?
So, so which one would be like um more or closer to biology case?
Well, you
It's
tell
like
me. What is different? That's why I'm asking you to think about it.
okay, okay. I haven't like thought about this before.
Well, if you're
So,
doing bacterial motion, this is a very fundamental aspect of bacterial motion. I promise you the one that I have on the screen is the one that's correct for bacteria, not the first one. Why? Think about it just for a few minutes, and then I'll give you a hint, and you can think about it some more.
okay.
Although, actually, the people in Riverside were doing simulations of bacteria, and also they had very detailed simulations of swimming of bacteria. And they behave almost exactly the opposite to what I'm saying that the bacteria should be doing here, as it happens. I think it'll depend on the kind of bacteria and their motility.
We're talking about single cell, right? So single bacterium
Mhm.
cell. Mm, the bacteria, the bacteria changes. I think because like the bacteria is swimming in the fluid,
Yeah.
and the fluid would just change the direction of their acting.
No, the fluid doesn't impose the direction. It can, but it's not what we're talking about. Fluid isn't moving.
But yeah,
Well,
like
there's no
there's a
bulk flow in the fluid.
bulk flow,
No flow. No flow.
no flow. So bacteria just like swimming in a medium or
Hmm.
like
In a
yeah,
non-moving medium.
yes, in a now moving. But when the bacteria is moving, like how does it acting perform? Because bacteria is it like relevant to its acting? For example, like flagella thing.
Well, sorry, what was that? But I didn't hear the first word you asked. Just
Oh, acting. So acting like um
well, so bacteria flagella aren't actin related, right? The eukaryotic movement is quite
oh
different from
eukaryote.
bacterial. Now, now,
Okay.
now, there are eukaryotes that have cilia, and so those are more like bacterial flagella. But normally, the eukaryotic cells move by protruding and retracting the cell membrane, not by spinning things. The difference is that bacteria have a rigid cell wall, so they can't move that way. So in bacteria, you have flagella, you have pili, you have a whole variety of movement apparatus. But just think about it this way. Not don't think so much about the way the machinery.
Yeah, because you said like in biology,
Hmm.
bacteria would like the speed vector would change
Hmm.
according to their
Yeah.
current speed.
Yeah.
So
Suppose that I have a cell, bacterial or not, and there's a wall,
Mhm,
and the cell is moving and it hits the wall.
mhm,
If the movement of the cell of the bacterium, of the direction of the force vector is random, then the force on the cell won't care that there was a wall or not. And in particular, it will keep trying to move through the wall, which it can't do. If the force vector aligns with the direction of movement, then the force vector will rapidly switch to be parallel to the wall. The cell can come off the wall, but it can't go through it. And so having the force vector track the direction of movement gives you much more rapid movement around obstacles. In one case, the direction of the movement around the obstacles is purely diffusive. In the other case, it's directed.
so like there's no like mechanical like mechanism explanation to that, but is that it's like a conclusion from our observation or
Well, in reality, what happens is that there are interactions through the fluid. There, I
yeah.
mean, in the case of bacteria, the direction of movement is fixed because the bacterium is fixed and the flagella are fixed in position. In the
Hmm.
case of eukaryotes, you actually get a change of the direction of extension. The polarization axis changes. And that
Mm-hmm.
happens if the cell runs into an obstacle and it can't extend actin in that direction, then it'll start extending it in a different direction.
Oh,
But this is more of an operational thing. You can try. It's a nice homework assignment to do this, which is to compare how fast the bacterium or cell moves across the wall when you have co-aligned movement and when you have random movement. And you'll find that in the case of the co-alignment, the cell moves along the wall quite quickly. In the case of random movement, the cell will move along the wall, but much more slowly.
um,
And what you would find if the cell were elongated was the cell would would align up parallel to the wall. Now, according to the experiments and simulations done by the people at Riverside, that's not what happens. Actually, the bacteria line up, go to perpendicular to the wall, and they stop moving. So they're swimming around, they touch the wall, and they try to swim into the wall, and they stop perpendicular. And I don't know because their experiments seem to be very accurate. But I've also seen situations in which what I'm describing happens, where you get flow along the wall. And I don't know what it is about the specific swimming mechanism, because that's what you were talking about, that leads some bacteria to go perpendicular to the wall and stop, and other species to swim parallel. I don't know what the specific aspect of the swimming is that does that. All we
yeah,
can do in our case is say, experimentally, you observe that you swim along the wall parallel, in which case you do this, or vice versa, you have their observation where you go perpendicular to the wall and then stop, in which case you need a different algorithm.
yeah,
And you could look that up. That's been studied a lot, so I'm sure there's a big literature on that. I'm not so familiar with that. And so, okay, and that's really as far as I was going to go today. We've gone through 3 hours, so I think it's probably enough. And here there's this comment about you see a switch from random to ballistic movement. So you can actually, this is a little exercise to try to measure the persistence time of the cells. And this is an exercise Pedro wrote, which is sort of nice one, which is a model of wound healing scratch assay, where you start out with the cells in a confluent layer, you get rid of the cells in the middle. And there's a very famous experiment due to Trepat. If you assume that only the cells on the surface of the wound respond to the wound, then the cells have to pull all the cells behind them, which is very slow. The wound closes, but very, very slowly. In reality, what seems to happen, and this was the observation of Trepat, is that the cells at the edge, they can't move in any direction except into the wound, because that's the only place there's room for them to move. When they move in that direction, there's this co-alignment, so they tend to keep moving in that direction. And they pull on the cells behind them and tell them to move in the same direction. And again, I gave the example the other day of, suppose you have a train where you have a locomotive in front and it's pulling lots and lots of cars, coal cars, that are not powered. Then the longer the train gets, the slower it's going to move, because the force at the front is fixed and you're distributing it over more and more drag. On the other hand, if you have something like a high-speed train or a subway car, the first car sends a signal to the second car telling it to turn its motor on and move in the same direction. So it's like many cars driving on the highway together, you don't slow down when you have more cars. And so what happens in wound healing, and this was what Trepat showed 20 years ago now, is that the first cells, when they move forward, instruct the second cells to move in the same direction, and then that's relayed back. And the result of that is that the wound closes very quickly. And so this is a simulation where the first cells start moving in, they lead the second cells to move in, and third cells, and so on. And so then you get rapid closure. And so again, I don't think we have time today to go through all of that, but it's a fun exercise. And you do see there are a lot of papers. You could see when this slide was done, 2020. It's called coordinated motion. So coordinated motion, coordinated motion, coordinated motion. So these are all articles that explore that. In fact, this is particularly nice simulation of exactly that. This modeling closure of circular wounds through coordinated cell-collected motion. And this is by Herbie Levine. That's a very famous computational biophysicist. He used to be at San Diego, and then he moved to Rice, and then he's now at Northeastern University. That's a nice paper to replicate. So I think for today, if that's all right, that's where we'll stop. I'm sorry we didn't have time to do these exercises, but at least you've seen we've talked about them. And now maybe I'll give you, next week is a holiday, so there's no class. I may write up for you, basically give you as a little assignment some of these exercises so you can try that out. And do try to go through that bacterium neutrophil, bacterium macrophage simulation. Because I think going through all those steps, learning how to use the manuals and figure out how to do these things, it'll be frustrating the first time you do it, it'll be slow. But once you've done it once, then when you have to learn new things about how to use it, I think it'll be faster. Okay?
Yeah.
Okay.
Thank you.
Anything else you want to go over tonight?
Think probably no. I think like for the previous assignments, which you left some comments on, I could just bring the spring holiday to go over them if some problems, if there is some
Right.
problems with the previous assignment, and I'll just keep developing
Right.
the code generator according to your
Right.
instructions.
Right. I
Yeah.
mean, I know if you're working on the project, you don't have infinite time. So to give you a lot of homework and give you the code generator is a lot to ask for. On the other hand, it's important to understand a little bit about how CompuCell works. Otherwise, when you do the code
Yeah.
generator, it's not going to be meaningful.
Yeah.
So I'm trying
Yeah.
to give you
I agree.
I'm trying to give you enough homework assignments that you consolidate your understanding of CompuCell without giving you so much that you have to spend all your time doing that. And so that's what I said before, that it's important to do enough of these exercises that you understand this is how chemotaxis works. This is what the parameters mean. But you don't have to get every piece of every exercise done. The point of the exercise is to give you a structure to learn about how these things work. If something is too time-consuming or confusing, stop and ask me or Pedro how to do it. Because the goal of the exercises is to help you learn to understand CompuCell. It's not to try to say you must get every detail right. And we tried to design the exercises so you learn simplest thing first, and then a little bit more, and then a little bit more, and then a little bit more, which is why there tend to be a lot of steps in the exercises. But they're also designed so that each step doesn't take too much time. Once you get the first one done, you do a little bit of an extension and see what happens. And it's also very important to do what we were doing together in class, which is try increasing the value of the parameter, try to see what happens. Try decreasing it and just play quickly. Try lambda equals 20. What happens? 30. What happens? 40. What happens? 50. What happens? You do have to learn how to look at the simulation and ask, what is happening? How do I describe what's happening? But the goal is not that these exercises should take very long. The idea of these sub steps is to help you think about how to look at the problem. It's not so they're not individually meant to be very time consuming. It's meant to give you some guidance instead of saying just explore what happens with the parameters, which is too many choices. Try to walk you through the critical things to look at. Okay? All right. Anything else tonight? I think
Yeah.
Pedro was going to his guitar lesson.
Yeah.
He plays the guitar and he sings, you know that?
I have no idea. It's wonderful.
There's a traditional style of guitar playing in Portugal. Well, actually, I said wrong. In Brazil, they have a traditional style of guitar playing and singing. Uh, it's not classical music, but it's also not pop music. It's a folk music tradition.
Oh, so where do you like learn guitar in Bloomington?
So I think he takes. I don't know if he's doing it in person. He was taking lessons still from Brazil.
Oh,
I think he also has a
incredible.
group here. I think he also has a group here in Bloomington that he plays with now in person.
Wow,
But he still has a teacher in Brazil who gives him lessons by Zoom.
wow, incredible. Did you
One
play
time,
any
one time
instruments?
he came. One no, I don't. I'm afraid. One time he came over for dinner, and then he brought his guitar, and after dinner he played, and he's very good.
Wow,
Uh, Sometimes he's a little shy about playing for other people, but if you ever meet him in person, you tell him you want him to play for you. He's really good. All right. Okay.
it's all right.
Well, great.
Thank
Well, thank you. And if I
you.
don't see you during the holiday, have a good break. Whether you get some rest, whether you catch up or something. But I hope not having. Well, this is the only class, so I guess it doesn't make much difference to your life if we have one class or not. But I'm going to be away again next week. But if you
Oh,
need me, I can always make an appointment and meet with you.
thank
Okay?
you.
Great.
Okay,
Okay. Thanks so much. Good night.
thank you so much. Good night too.